Welcome to this video for statistical modeling at HEC Montréal. In this recording, we will look at log linear models, so how to handle counts that are displayed in contingency tables and how to test for independence. Okay. So what is a contingency table? Essentially, it's a format in which the data, rather than being in long format, right, one response per line, with additional columns for the different levels of categorical variables, are displayed in a table. Okay, so you see here we have a two-way contingency table. The rows denote the different levels of one of the categorical variables. The column gives the same thing, but for the second. Okay, so here I'm assuming the one of the categorical variable has J level and the other has capital K. And so each entry in this table represents the count. Okay, so there's a total of K times J observations here in the model with two categorical variables. And so how do we model this? Well, we have two explanatory variables. So there's a couple of models we can envision. One in which we basically say there is no impact. So that's the intercept only. The mean number is the same for every cell. Then there's one in which there's an effect, but only for rows. Then the model with only an effect here for columns. And finally, the model in which there's an effect for both row and column. The final model, which we will not be fitting, is the interaction model. And that basically amounts to having a different mean for every subgroup, much like we would do in a two-way analysis of variance with an interaction term. Here the difference is that, of course, because these are counts, we would have as many parameters as we have observations, hence this interaction model corresponds to the saturated model. Okay. So we will be considering model selection and see how we can handle this. So the model is of the following form. Here I'm changing the betas to have two other variables so that we don't get mixed up with the effect. Okay, and so we will employ the typical parameterization I am including for the mean, an intercept, beta naught, and each of the categorical variable, if I'm putting the main effect only, so additive, has here J minus 1 and K minus 1 parameters, one for each of the different effects. Okay, so we fixed one of the, basically one less parameter per categorical variables than the total number of levels. Okay, so we're going to fit a log linear model. You could also so here I'm going to stick with the Poisson, but there are also other alternatives. If you wanted to fit a negative binomial model, this is also an option. So here I have the additive model, okay, so both main effects, and I'm going to compare this to the saturated model, which includes an interaction. And the model with main effect only, basically saying there's an effect for every observation in a row, in a particular row. It's all the same. And there's the similar effect for every observation in a column, and it's all the same. And so if I assume there is no interaction, this is what we call a test of independence. And that amounts to saying that the parameters with the interactions are 0. And we already know how to test this, right? I could fit both model, saturated model and the main effect only model with both categorical variables, and do a likelihood ratio test here. Okay, and so if you were to actually compute, as I said, the maximum likelihood estimator of this interaction model, you would realize that basically the answer is every fitted mean would correspond to the actual number of observation in the cell. So we do not need to fit the model with J times K parameters because the fitted value are simply Y, J, K. And because we have in the output already this Pearson X2 and the deviance, these are actually the likelihood ratio statistic for comparing this interaction model with the main effect model only. Okay, so just a brief reminder, because of the particular form here, this would be the deviance if I had to compute it manually, where mu hat is the value under the simpler model in which there is no interaction term. And Pearson X square statistics, as I said, would take a much simpler form here. Okay, if you plug in the Pearson residual, compute the score. For the Poisson model with canonicalling, things simplify quite a bit. So you may have seen this test statistics, one or the other, in other courses, and we have them directly, as I said, in the output. So let's consider an example of a contingency table. I'm showing you, so this has 2 categorical variables with 2 and 3 levels. So there's 6 entries, and then you can look up the row totals and the column total and the overall number of people that were asked what were their political affiliation in 2000. So there's 2,757 people. But if you consider this as Poisson data, there's 6 observations, okay, which are the entries in, so that's 762, 327, 468, 44, 239, and 477. The value in parentheses just below these counts are the average predicted from the main effect model only. Okay, so if you just included an effect for Democrats, Independent, Republican, male, female. So of course we don't have the same number of men and women in the sample, but if there were independents, we would assume that notably we'd have the same proportion. Okay, and so testing independence amounts to saying, is this the case, or is there, for example, here seems to be more Democrat women than men, okay, in terms of proportion. So we can use the GenMod procedure, and this is selected output. So you would see the test statistic has a value of 30 against 2 degrees of freedom, and we expect this to have on average, if the null was true and there was truly no difference between gender for political affiliation, so no interaction term, we would expect it to be about 2. Okay. So if you compute the p-values, find something that's very tiny, less than 10 to the minus 4, and thus we would reject the null of independence. So analysis of variance and basically linear models with 2 categorical, or you could have extensions to higher dimensions. Okay, but these 2-way ANOVA models have a direct analog for count data using a Poisson model in contingency table. Except that there's very few entries here. And so we can use our likelihood tests again to compute these. And here we seem to have a conclusion that gender has an impact on the political affiliation.